In the movies, a single drop of glowing green acid lands on a spaceship floor, hisses, and eats straight through the solid hull in seconds. In reality, chemical destruction is much slower and highly conditional. When you put the fiercest acids up against sheer thermal energy, like thousands of degrees of molten lava, the results often defy our expectations. You've probably seen viral videos of a metal spoon vanishing instantly into clear liquid, seemingly proving that chemicals can melt anything on contact. That trick relies on a specific property of the material. The clear liquid is often just warm soda, but the spoon itself is cast from gallium, a metal with such a low melting point that it turns to a liquid at lukewarm temperatures. True destruction depends on the precise interaction between an attacker and a target's internal structure. If the incoming force cannot find a specific vulnerability in those molecular bonds, the material remains intact. Let's look at organic matter. Flesh, bone, and muscle are built from complex, carbon-based biological structures. Massive pores of molten lava seem like they should obliterate organics instantly. Instead, the magma sears the immediate surface and rapidly cools into an insulating crust. It fails to achieve deep thermal penetration, leaving the interior largely untouched. Switch to chemistry and the results flip. Over a few hours, hydrochloric acid systematically breaks down those complex organic tissues. It is a terrifyingly efficient process, mimicking the exact chemical digestion happening inside your stomach right now. Biological structures are also susceptible to mechanical stripping. A school of hungry piranhas can tear an organic target down to the bone in less than 60 seconds. Organic material relies entirely on maintaining its chemical integrity. Once you introduce a corrosive agent or a sharp tooth, it acts as a soft target and rapidly falls apart. Dense metals and sophisticated electronics present a different challenge. Hit a complex device with extreme thermal shock, and the result is catastrophic. The internal architecture melts down almost immediately. Standard acids fail against dense metallic structures. The atomic grid holds firm. To begin a reaction, you must mix hyper-potent chemical cocktails, like aqua regia. Introducing heat accelerates these molecules, giving them enough kinetic energy to start ripping individual metal atoms away. Yet, even accelerated, boiling acid struggles against sheer scale. Dumped over a functioning car engine, the chemical assault eventually stalls out. The pure mass of the metal simply outlasts the chemical reaction. Tightly bound metallic networks stall chemical theft. To defeat them quickly, you have to rely on extreme heat or the brute physical force of heavy machinery to break those bonds apart. Here, we have a collection of cheap synthetic plastics. When you douse them in highly concentrated, boiling acid, you expect an immediate meltdown. The acid rains down, pools around the plastic, and does absolutely nothing. The toys remain perfectly intact. Synthetic polymers are built from stable, tightly intertwined, long-chain carbons. Because those atomic bonds are already fully satisfied, they offer no weak points for the acid to latch onto. They effortlessly repel the chemical attack. Because of this molecular stability, the same concentrated acids that can eat through solid metal are safely stored, shipped, and sold in thin plastic bottles. Synthetic polymers shrug off chemical warfare. It is the reason they sit fully intact in landfills for millennia. To break them down, you must rely on extreme thermal melting or the massive kinetic crushing of an industrial shredder. Water presents its own set of bizarre reactions. Pour concentrated acid over solid ice, and it doesn't just sit on the surface. As the acid mixes with the melting water, it triggers an exothermic reaction. The mixture generates intense, localized heat, boring a deep hole straight through the ice. To find the absolute limit of material science, we have to look at a pure carbon allotrope, a diamond. The carbon atoms in a diamond form a flawless, three-dimensional geometric lattice. This architecture allows it to shrug off thousands of degrees of thermal shock, concentrated acid baths, and blunt physical force. Ultimate physical resilience does not require raw weight or massive density. It is a product of the geometric architecture of atoms. Hollywood has conditioned us to believe in the universal destroyer, a glowing liquid or superheated ray that melts absolutely everything in its path. True vulnerability and indestructibility are dictated by a rigid physical negotiation. It always comes down to the exact relationship between the attacker's method and the specific molecular bonds of the target. Mastering the physical world requires understanding the geometry of its construction. Only when you identify the specific arrangement of atoms do you know exactly which force is required to break them.